All right, hi guys. So this is lesson 2.7, proving segment relationships. So this PowerPoint, this video is going to be just the 3 proofs we did in class. So it's not going to have any of the other definition stuff that you can find in your textbook. Okay, so this video is only the proofs. Let's get started. All right, so this first one. We are using the segment addition postulate. As a reminder, that is going to be something along the lines of AB plus BC is equal to AC. Okay, something along those lines. So, we are given in this proof, JL, okay, is congruent to KM. All right, and we want to prove, I'm going to use blue for what we want. Actually, no, I'm going to use yellow. I'm going to use yellow for what we want to prove. We want to prove that JK is congruent to LM. Okay? Now, the yellow stuff is where we're trying to go. We haven't gotten there yet. So I'm going to make some notes off to the side. Now, I see I have JL. Well, let's explore what we know about JL. Okay? We know that JL is going to be equal to JK plus KL. And I know that due to the segment addition postulate. Okay? And by that same postulate, I know that KM is going to be equal to KL plus LM. Okay? Now, as I'm looking at this, I notice that they both share this piece KL. And as I think about this, if JL, that whole segment, is equal to KM, that whole segment, and they both have this shared piece, then I can take away that shared piece from both of the equations, leaving only JK and LM, which is what I want. All right, so that's the direction I'm going to go in. I'm going to try to set up these equations and then take away KL. So let's go down to the proof. Now, we already have this set up for the most part. Statement A was always going to be our given. So we have JL is congruent to KM. And then we went from the congruency symbol to equal signs. And this is because of the definition of congruency. Now, the reason why we need equal signs is because our segment addition postulates have equal signs. So we need to transfer our symbols. Step C is our segment addition postulate step. We're asking ourselves, what do we know about JL? And well, we know that JK plus KL is JL. And we know that KL plus LM is KM. This is the segment addition postulate. We're breaking down what we know about each of those whole pieces. All right. Now, let's look at this. Since we know, Since we know that JL is equal to JK plus KL, I can take this information and I can plug it in. I can substitute it for JL. So this property right here is going to be substitution. So JK plus LK goes in place for JL. And then I have KL plus LM being substituted for KM. And that's how we get this statement down here. It's all just been substitution. Now, up here, right now, I'm going to add a step. So I'm going to change colors. I'm going to add a step right in here. I'm looking at my equation, and I notice that I have KL in both spots. Now, if I subtract KL, I'll be left with JK is equal to LM, and that's what I want. So I want to subtract KL. But because KL is in 2 parts of the equation, before I can subtract it, I need to say that KL is equal to KL. Yes, I know this is very obvious. It falls into the no duh category of math. Of course KL is equal to KL. That's obvious. But the thing is, it's not. This is the reflexive property. Okay? KL is in 2 equations. It is in 2 separate equations. We are trying to subtract it. The only way you can subtract something is if they are equal. Because KL is in two separate equations, we have to state that KL is equal to itself. That way, we are allowed to subtract it the way we want to in this next step. Okay, because you can only subtract the same thing from both sides of the equation. All right, once I subtract it, I am then left with JK is equal to LM, which is what I wanted. But my proof has congruency symbols. So I need to change that, and I need to have it as a congruency symbols. And that's this last step. JK is congruent to LM. All right, and that is this proof. Now, for the most part, it's fairly easy to follow along. I think the only curveball for you is the whole KL and the reflexive step. But remember, in order to add or subtract anything from both sides of the equation, it has to be the same. You can only subtract the same thing from both sides. You can only add the same thing from both sides. So before you can go subtracting or adding symbols, you have to state that those symbols are indeed the same thing. Before we move on, I'm kind of out of space here, so I'm going to sign off over here, but always make sure you sign off. All right, let's go on to the next one. Now in this one, we're given that SU is congruent to LR. Okay, so I'm going to annotate that as best as possible. SU is congruent to LR. And then we're told that TU is congruent to LN. Let me use yellow again. We want to try to prove that ST is congruent to NR. Okay, so let's go ahead and get started. So first off, this is always my given. You're going to start off with your given. Next, we have a little hint over here, but we are going to need to switch this into equal signs. Okay, again, the segment addition postulate uses equal signs, so we also need equal signs. So SU is equal to LR, and then TU is equal to LN. There we go. Now this next bit is segment addition postulate. Okay, so we know stuff about SU, we know stuff about LR. Okay, so here it is. We know that SU is equal to ST plus TU, and that LR is equal to LN plus NR. This is the segment addition postulate. Okay, now what I'm going to do is I'm going to take each of my pieces and plug it into the equation for their whole. Okay, and that's how I get this D line. This would be substitution. I have taken my pieces and I've plugged it in to the whole equations. And look, now I have an equation and I can maybe subtract some stuff. Okay, now remember on the last one where I said you had to state that things were equal first before you could subtract them? Well, this proof does that in a slightly different way. So instead of just subtracting TU and LN, they substituted LN for TU. Okay, so we know that TU is equal to LN, so they plugged LN, they substituted one in for the other. That way they could subtract LN from both sides. Okay. Subtraction property of equality. Because again, you can only subtract the same thing. So they substituted LN for TU, and now we can subtract LN from both sides of our equation. When we simplify, we are left with ST is equal to NR. And then we use the definition of congruency to change that equal sign back to a congruency symbol. And then we always sign off. Okay, and that's this proof completed. All right, last proof. Now this one doesn't have any fill in the blanks, so we got to go from scratch. Here we go. So I'm told that CE is congruent to FE and that ED is congruent to EG. Okay, and now somehow I need to get that CD, which is the whole segment, is congruent to FG, the other whole segment. All right, now this one is different because the other two, we were given the information about the wholes and we were subtracting pieces. Okay, now we're only have information about the pieces and we've got to get to the wholes. Okay, so we're still going to be using segment addition postulate, but it's going to look a little different. Okay, let's go ahead and get started. So I have that CE is congruent to FE. And then I have that ED is congruent to EG. And this is my given. Next, because I know the segment addition postulate's coming up, I'm going to transfer all of those congruency symbols into equal signs. So I've got CE is equal to FE. And then I've got ED is equal to EG by the definition of congruency. All right, now remember what I was saying about the addition, subtract, and subtraction policy, our properties, okay? You can add or subtract the exact same thing to both sides of the equal sign. So I'm going to change color so you can see what I'm doing. I'm going to take this right here. Okay, I have CE is equal to FE. I'm going to put it down there. Now, by rule, by the segment, by the addition property of equality, I can add the same thing to both sides of my equation. ED is equal to EG. Those two things are equal to each other, which means they are the same. So I can add ED to this side of the equation, and I can add EG to this side of the equation. Okay, so I took my two equal pieces and I added two more equal pieces on either side of that equation. Now, I hear you asking through the screen, why did you do that? Well, let's look at where we're trying to go. I'm trying to get CD and FG somehow. Okay, well, by the segment addition postulate, I know that CD is equal to CE plus ED, and I know that FG is equal to FE plus EG. All right, this is the segment addition postulate. Okay, notice, hopefully you've noticed, but notice how this is the exact same thing as this. And notice how this is the exact same thing as this. Which means that I can plug in CD into my equation, and I can plug in FG into the equation. Okay, I'm going to change color so you can see what's going on. So I now have CD is equal to, all right, FG after all is said and done. And I know this because of the substitution property. That's why I'm allowed to do this. Okay, so I had my segment addition postulate, and then I was able to plug the whole segments in for the expressions of their sides, or the pieces. Okay, and now the last thing I got to do is change that equal sign into a congruency mark. So I have CD is equal to, or is congruent to, my bad, FG, and this is the definition of congruency. Okay, so this one was a little bit different. Instead of going from the whole segment to the pieces, we went from the pieces to the wholes, but hopefully you were able to follow along. If you have any questions, please let me know. Don't forget to sign off, and I'll see you next time.